So I'm going to be looking at some properties of polynomial functions. Now, it's really important that we are able to recognize the degree, the largest exponent. So I'm just going to say, suppose the degree is n. The maximum number of turning points is going to be n minus 1. The maximum number of x-intercepts, or 0, is n. So I'm just going to drop over to my previous video or my previous screen here. Now, this is a degree 5. It's called a quintic function. And if you spot out the number of turning points, you're probably able to see quite a few. So for instance, there appears to be a turning point there, there, and there. So this is degree 5, but it has 4 turning points. Well, that was fairly nice. The number of zeros we have is 1, 2, 3. Now that's not surprising, but there may not be a connection between the degree and the number of zeros. So if I take a look at something a little bit more ridiculous. Quadratics, always ridiculous. The number of turning points on my quadratic function here, well, there's 1 turning point. This is degree 2, but it still has 1 turning point, 1 vertex. Now, what I notice is that my parabola has 2 zeros. So it's degree 2 here, but I have 2 separate zeros. So let's go back to those rules again. And if I have a degree n polynomial, the number of maximum turning points is going to be n minus 1. The maximum number of zeros is n. Now, if the degree of my function is even, the left-hand and right-hand side behavior mimic the behavior of other even degree functions. Now, an even degree function is a quadratic. You're an expert in quadratic functions? Great. Hopefully, we're able to make connections with the left-hand and right-hand side behavior if we look at the degree and the leading coefficient. If the function has an odd degree, the left-hand and right-hand side behavior mimic the behavior of those of other odd degree functions. Now think linear, right? Linear is an odd function and you're an expert in that. By the way, the y-intercept is at a0. Let's get started. So here's a constant function. The degree of a constant function is 0. I'm just going to write y is equal to 3. This is degree 0. The number of turning points is 0. The maximum number of zeros, I'm going to put a star there. So I'm just going to draw 2 Cartesian planes. I'm going to zoom in, concentrate our conversation here. Y is equal to 3 looks like this. It's a horizontal line. This is a degree 0 because the largest exponent here is x to the power 0. There are no turning points on my graph, and the maximum number of zeros is 0. Similarly, I could have y is equal to negative 4, and that would be a horizontal line down here below the x-axis. All right, a linear function, something that you guys are masters of. So here's my x and y plane. I'm just going to make little pictures here. And I'm just going to say a linear function can look something like this. Or a linear function can look like this. So we can have a positive slope or a negative slope. The degree here is 1. So I'm just going to write down an example. Y is equal to 2x plus 3. The exponent for a linear function is 1. Now, how many turning points on a line? There are no turning points, or you can think vertices. The maximum number of zeros we can have on a linear function is 1. All right, let's go. Quadratic function. Now, I'm just going to make graphs here, and we're going to talk about quadratic functions and some things. And I just want to get you familiar with what we're talking about above. So a quadratic function can look like this. Quadratic function can look like this. Or a quadratic function. Now, these are not the 3 patterns of quadratic functions, nothing near that magical. But a quadratic function has degree 2. The number of turning points or vertices on a quadratic function, there's 1. The maximum number of zeros. Well, there are no zeros there. Here, there are 2. And on my last bottom picture, there are no zeros. Or sorry, 1 0. So the maximum number of zeros is 2. A cubic function. Well, a cubic function are fairly interesting, I think. They need not be symmetric in any way. So a cubic function can look like that. A cubic function could also look like this. So the degree of a cubic function, well, the highest exponent is 3. The number of turning points is going to be 2. The maximum number of zeros is 3. Now, it depends on the equation. We have a degree 3 function here because the highest exponent is 3. But the maximum number of turning points, for my first graph, there are no turning points really to say. But on the second graph, there's 2. So that's why there's a maximum of 2 turning points. Maximum number of zeros or x-intercepts, there's 1, 2, 3. It's going to be 3. So the turning points matches the degree. The maximum number of zeros matches the degree. So, sorry, the turning points is 1 less than the degree. So a quartic function, I'm just going to graph a quartic function. I'm going to just graph 2. I think you're maybe getting the hang of this argument. A quartic function, this is just the beginning. It can look like this. Oh, that's it. There. It behaves like a even degree function, a parabola. Left-hand and right-hand side behavior both point the same way. We can discuss that more in class. So this is a 4th degree function. The maximum number of turning points is 3. The maximum number of zeros is going to be 4. However, I want to introduce you to the notion that y is equal to x to the power 4 will just look like a parabola. All right, a quintic function. Well, it doesn't, hopefully we're starting to get a flavor for what's going on. A quintic function, it's an odd degree. So I'm going to make a quintic function. I believe that would be a quintic function. So how many turning points on there? 4. 1, 2, 3, 4. Certainly looks like a quintic function. So that's the maximum number of turning points. How many zeros do we have? 1, 2, 3, 4, 5. So the degree is 5. The maximum number of turning points is 4. The maximum number of zeros is 5. But keep in mind that there's always exception to the rules. A quintic function can also look like this. Oh, right. Well, what was the whole point of this when there seems to be almost no pattern? Well, there is a pattern, and we're going to have to take a closer look of what's going on in here. Our strategy going forward is basically to talk about the left-hand and right-hand side behavior of a graph. Does the left arm point up or down? Does the right arm point up or down? And we can determine that. The next thing that we're going to be doing, and this is for later in the unit, it's going to take a lot of work to get there, we're going to find the zeros of the function. And how do we find zeros of a function? Well, hold on. Y is equal to x squared minus 6x plus 5. What are the zeros or the x-intercepts? You would probably factor it, wouldn't you? Well, how do we find zeros of something really nasty? Please don't try to factor this. Not yet, anyways. How do we do it? We factor it. All right, there's still more coming.